Hello, I'll be talking about our work on verifying properties of bit vector multiplication using cutting planes reasoning. I'm Vincent, and this is joint work with my co-authors Paul, Yo, Jan, and Jakob. So to start off, this work is geared towards the application of bit vector solving. The question in bit vector solving is, given a bit vector formula phi, we want to determine whether or not it's satisfiable. So bit vectors, they pose an interesting challenge for automated reasoning tools because we sort of have two ways that we can look at a bit vector. So from one perspective, we could look at a bit vector as being just a string of ones and zeros. And in this view, we can apply bit level operations. For example, we can apply bitwise AND, or we could apply bit shift, or we could extract a substring of a bit vector. Another way that we can view a bit vector is as a representation of an integer. And from this perspective, we can apply arithmetic operations like plus and multiplication. The challenge here is, though, that a lot of the time the methods of reasoning that work well with the bit level are not so fast at handling word level arithmetic reasoning. And conversely, the methods that are good for handling word level arithmetic tend to not do so well with bit level logic. And this manifests in an important bottleneck that comes up in practice, which is the presence of bit vector multiplication, especially when this multiplication is combined with bit level operations. So current bit vector solvers are actually quite fast at handling the other arithmetic operations, such as addition and subtraction. But when we're trying to verify a larger system that includes multiplication as sort of a relatively small component, these solvers really tend to hit a wall. A lot of the time, there's a manual effort that we need to do in order to work around multiplication. For example, sometimes multiplication, we treat it as an uninterpreted function that just satisfies some sufficient set of basic properties. So what causes this bottleneck? Well, the dominant way that bit vector solving goes is as follows. So the first step is to preprocess the input formula and simplify it as much as possible. And generally speaking, in this step, some word level reasoning takes place to do these simplifications. And then in the next step, we bit blast the simplified formula, which means that we take the bit vector formula and convert it into a SAT formula, which is then given to a SAT solver to give the final answer. So if we see arithmetic operations such as addition and multiplication, well, of course, we're going to need a way to represent these things in CNF form in order to make use of a SAT solver. And the way that this is done is to use a circuit implementation. But unfortunately, SAT solvers, it's well known that they're especially bad at reasoning with multiplication circuits. And since current SAT solvers use, they all really rely on SAT as their back end, they end up not being so effective with multiplication because of this weak point of the SAT solver. In fact, even one of the most basic properties of multiplication, commutativity, is already hard for SAT to verify. So say we construct the following SAT instance, which consists of two multiplier circuits, one taking in the inputs x and y, and the other taking in the same inputs but in reverse order. And at the bottom we have some logic that asserts that the outputs of these two multipliers are not equal somewhere. It was observed in 2016 by Bierre that no matter which combination of SAT solver or multiplier circuit you use, it seems that this problem becomes intractable beyond about 16 bits. Okay, furthermore, the runtimes here, they seem to grow exponentially with the number of bits. So, for example, you can see in these runtimes from when I ran Minisat on my own laptop, I wasn't really able to get past 10 bits or so. You can see as with each increment in the number of bits, you can see that the time it takes to solve more than doubles with each increment. Now, Minisat is a relatively old SAT solver, and solvers have definitely made big general improvements since then. Okay, but for some reason, multiplication problems they seem to have largely resisted the effects of these improvements. And actually, even if you take a current cutting-edge SAT solver, it's not going to do much better than Minisat does here. So since SAT solvers, they don't really seem to know that bit vector multiplication is commutative, it's really left up to the preprocessor to apply this commutativity property wherever it's needed in order to simplify the formula. Okay, so if the preprocessor fails to simplify a formula enough, it's very easy for the SAT solver to get sort of trapped in this, sort of get trapped in reasoning about these multiplier circuits. And this picture, it's actually quite similar with all the other word-level properties of multiplication. For example, each of the ring properties, commutativity, distributivity, and associativity, is hard for stat solvers to verify. As a consequence, a bit vector solver is generally going to rely on its preprocessor in order to make use of these properties of bit vector multiplication. Okay, this method is good enough to handle some isolated multiplier properties, for example, distributivity. No stat solver would be needed here because preprocessing, rewriting, will just make the problem trivial. For more complicated systems, especially those that involve a mixture of multiplication and bit-level operations, preprocessing is often not really enough to avoid needing to bit blast to a stat solver in the end. Whatever set of rewrite rules that we come up with for the preprocessor, they can't possibly cover every situation that can come up. It seems that if we're going to handle these larger multiplication problems, we're going to need to face this bottleneck head on. We ultimately need to improve on the back-end reasoning. And the hope is that improving on this back-end will relieve some of the burden on the preprocessor. So, can we improve on the back-end stat solver? To answer this, we need to look more closely at the limits of stat-based reasoning. We're going to explore this idea by taking a proof complexity theoretic perspective. It's rather well known by now that modern stat solving is based on the resolution rule. And the important thing about this rule is that we can use it to prove that a formula is unsat. So, for example, on the left here, I've taken this formula phi, which consists of these bottom four clauses, and I've used the resolution rule in order to derive the empty clause up top. So the key connection between resolution and stat solving is that whenever a stat solver outputs unsat, it must have walked through a resolution proof beforehand. So if it takes time s for a stat solver to prove that phi is unsat, then it must have walked through a size s resolution refutation. Okay, so given this connection, we want to know, okay, what proof sizes can resolution achieve for, say, the properties of multiplier commutativity or distributivity? Well, currently, the smallest known resolution proofs for multipliers are given by some of our prior work. To sum it up, we found that resolution is capable of polynomial-sized resolution proofs for any degree 2 multiplier identity. Okay, so for some concrete examples, this theorem gives an O of n to the 6th size proof for multiplier commutativity, as well as distributivity. And for other more complicated identities, the size of these proofs can get a lot larger. Okay, so if these are the smallest proofs that resolution has to find, then it's really no surprise that stat solvers struggle so much with these properties. Even if they had so-called optimal heuristics for proof search, just walking through these proofs would take way too long. So the natural question to ask then is, what if we move to a stronger proof system that could produce much smaller proofs? We'll focus on two proof systems that are stronger than resolution, and these are polynomial calculus and cutting planes. Okay, so first, let's discuss polynomial calculus. So the polynomial calculus proof system is defined like this. For each line, we have a polynomial equation. We set p equals to 0. And we have two rules. We have the addition rule, where we can add two polynomials. And we have the multiplication rule, where if we know that one polynomial is 0, then if we multiply by any other polynomial, then the result should still be 0 as well. Okay, so this proof system originated in order to model the steps of Grubner basis reduction algorithms. Okay, so these are algorithms that, given a specification polynomial, p, it checks whether this polynomial is implied by a list of constraint polynomials, p1, p2, and so on. So you might think that since polynomial calculus is stronger than resolution, well, shouldn't Grubner basis reduction be more efficient than SAT? Well, it turns out that the answer is no for most non-algebraic problems, especially when there's bit level or Boolean type reasoning involved. SAT solvers are just orders of magnitude more efficient than Grubner basis reduction. However, if you find certain algebraic problems, Grubner basis reduction turns out to be quite a lot better than SAT. And in particular, a recent line of work was able to use Grubner basis reduction to achieve efficient verification for correctness of a great deal of different isolated multiplier designs. So in 2016, Syed et al. Were able to use Grubner basis reduction to verify 128-bit integer multipliers. And this approach was refined over the next few years by Kaufman et al.'s work. and they were able to push this up to verifying multiplier correctness for up to thousands of bits. So how did they do this? Well, it turns out that they're just very, very short polynomial calculus proofs. They're short polynomial calculus proofs not only for correctness, but also for other multiply properties. For example, in 2019, Kaufman gave a quadratic length proof of commutativity at the word level, which means that they were able to derive this equation, which says that the value held in the bit vector xy is equal to the value held in the bit vector yx. This proof idea can be further generalized in order to give quadratic length proofs for actually any word level ring identity involving plus and times. Right? So far this sounds pretty good for polynomial calculus. So could this be the form of reasoning that's the key that allows us to solve these bit vector formulas of multiplication? Well, not so fast. We found a proof complexity obstacle to this approach of using Grubner basis reduction. Okay? And so we showed the following theorem, which says that a polynomial calculus requires an exponentially large proof in order to derive any individual equality between the pair of bits between xy and yx. Even if we're given this equation that says that xy and yx have the same value, we can't deduce that the individual bits are equal efficiently in polynomial calculus. So this could very well be a fundamental obstacle that could prevent us from extending these Grubner basis methods, which were able to handle isolated multipliers efficiently, to solving larger bit vector formulas that could potentially contain both multiplication and bit level logic. The question is, could there be a proof system that does both? Well, maybe you can guess the answer from the name of this talk. Now we'll show some of our results to say that cutting planes as a proof system may have the potential to achieve this. Okay, so what are cutting planes proofs? Well, in cutting planes, each line L is a Boolean linear inequality. So we have coefficients AI that are all integers, and each xi is a Boolean variable, 0 or 1, and this b is an integer. So cutting planes has two rules. We can do linear combination as long as it's non-negative. So we can take two linear inequalities and add them together. The second rule is the division rule. So if we have an inequality and all of its coefficients are divisible by the same factor c, then we're allowed to divide through by that common factor c. So on the left, we'll end up with this integer expression where each ai is an integer. Okay, and on the right, we'll end up with this fraction b over c. Okay, and now since the left-hand side is always an integer, we can just round this fraction up without losing any solutions, without changing the constraint. Okay, so the cutting planes proof system is what underlies this approach of conflict-driven pseudo-Boolean solving. So this is sort of a generalization of conflict-driven SAT solving, but lifted up into the sort of the pseudo-Boolean arena. So right now, there are two conflict-driven pseudo-Boolean solvers available. There's SAT for J, which came out around 2010. Then there's a newer pseudo-Boolean solver called rounding SAT, which came out in around 2018. So how does cutting planes and these solvers do with this bit extraction problem, which we proved before was hard for polynomial calculus? Okay, so say we derive the following word level equation that says that xy equals yx. So on the left, we have the value of the bit vector xy, and on the right again, we have the value of the bit vector yx. And keep in mind that in cutting planes, we're working with inequalities. So whenever we write this equation in cutting planes, what we really mean is the two corresponding linear inequalities. And it's not too difficult to show that cutting planes is a very small linear length proof that can actually extract all of the bit equalities that go along with this word level equality. And furthermore, current pseudo-Boolean solvers are actually really good at finding this small proof in real life. So for example, we can see that the solver rounding SAT here, we were able to get up to an n of 256 and more with no problem at all. You can see that these solve times look about linear in n. And the use of cutting planes reasoning here is really crucial to obtaining these good solve times. Okay, so if you compare with the resolution-based pseudo-Boolean solvers, if you run any of those on this problem, they'll fail miserably. Okay, like we couldn't get any of these to reach even just 32 bits. All right, so great. Cutting planes, in contrast to polynomial calculus, can actually go from word level equalities to bit level equalities, and furthermore, we can do it very efficiently. So the natural question is it also possible to efficiently derive the word level equalities as well? How do the proof sizes scale in cutting planes? Well, we sort of answered this with the main theoretical contribution of our work. So we were able to show the following theorem, that there are quadratic length cutting planes proofs for word level two colorable ring identities. Okay, so what are two colorable ring identities? This is something we defined. This is a broad class of ring identities, and the exact definition here is a little bit involved, but for example, it includes identities such as commutativity, distributivity, generalizations of distributivities, and also things like distributing and then factoring. So basically, this theorem is saying that for this large class of two colorable ring identities, cutting planes is just as efficient as polynomial calculus. Now, it was somewhat expected that polynomial calculus would be a good proof system for multipliers since it's an algebraic kind of proof system, so it seemed like it's a natural fit. But with cutting planes, this result is kind of a surprise because cutting planes is really an inherently linear proof system. So the fact that it has such small proofs is kind of exciting because we saw in practice that the polynomial calculus proofs were actually small enough, quadratic scaling was small enough to allow Grubner basis methods to be very efficient in real life. And actually, cutting planes can go even further than polynomial calculus on these identities. As we saw in the last slide, cutting planes is an easy time going from the word level to the bit level. So using cutting planes, we can also derive each of the bit level equalities associated with these identities as well. So for example, the problem of showing that just the middle bits are equal on both sides of, say, this bottom identity, the proof size in cutting planes is actually a lot better than what we know for either resolution or polynomial calculus. So how did we do this? How did we do this nonlinear form of reasoning within a linear proof system? The key idea is to only use a little bit of nonlinearity at any given time. Okay, so to capture this idea a bit more precisely, we defined a new nonlinear format that you can use for writing cutting planes proofs. Okay, this format we call KD cutting planes. Okay, so recall that in cutting planes, we work with linear inequalities. In KD cutting planes, we're going to generalize this a little bit to KD nonlinear inequalities. Okay, so these are almost linear inequalities, but we're allowed to put in up to k terms of degree d or less. So remember that cutting planes had two inference rules. We had linear combination and division. Okay, so how do these generalize to KD nonlinear inequalities? Well, first, linear combination generalizes quite naturally. We're allowed to do non-negative linear combinations of KD nonlinear inequalities as long as the result is also KD nonlinear. So we can't have too many nonlinear terms accumulating on each line. The division rule also generalizes essentially immediately. There's no extra restrictions here. And lastly, we also include a multiply by a variable rule. So if we're given an inequality, we're allowed to multiply through by a variable as long as the result is KD nonlinear. Okay, so I said that this is a format for cutting planes proofs. So that means that if I'm given a KD cutting planes proof, then I should be able to convert it into a standard cutting planes proof without too much overhead. Our next result shows that this is indeed possible. So we showed the following simulation theorem. We showed that a KD cutting planes proof that's s lines long can be simulated by a standard cutting planes proof of at most k plus 4 times d to the k times s lines. So we applied this simulation in order to give the small proofs for these two colorable identities on the word level. So the way that we did this was we gave quadratic length KD cutting planes proofs where we were careful to make sure that k and d were held constant. Okay, so since k and d are constant, our simulation only has a constant factor of overhead. So these quadratic length KD cutting planes proofs turn into quadratic length standard cutting planes proofs. So this gives the following theorem that there are O of n squared length cutting planes proofs for word level two colorable ring identities. Okay, so with these small proofs in hand, how do cutting plane solvers do in practice? As we mentioned before, there are currently two modern pseudo-Boolean solvers that are able to find cutting planes proofs. The first was Sat4j, which is saturation-based and which we found worked better for the word level proofs. and rounding SAT, which is division-based and which we found worked better for the bit-level proofs. Using a combination of these two solvers, we're actually able to verify commutativity for up to 256 bits at the bit level. We were also able to efficiently check the equivalence of array and diagonal multipliers. These times were roughly comparable to those of the Grubner basis approach for word-level identities, which is pretty nice to see, as it kind of confirms that this quadratic scaling of these cutting planes proofs does reflect some real-life potential of these pseudo-Boolean solvers to be very efficient on these multiplier problems. However, these solvers aren't exactly all the way there yet. We weren't able to efficiently deal with more complicated two-colorable identities such as distributivity, even though they had small proofs. In the course of doing these experiments, we realized that cutting planes is a format that actually allows us to take a kind of different approach to bit blasting. Okay, the key advantage of this pseudo-Boolean format is expressiveness. For example, we can represent addition, x plus y, without even using a circuit at all. So all we need to do is write down this linear equation, and we fully represented this addition of bit vectors in a very natural way. Okay, in SAT, you'd have to use a circuit in CNF form in order to represent addition. Going even further, it's possible to represent multiplication without a circuit as well. Okay, all we need to do is use these n-squared tableau constraints to set the partial products, and then we can write this equation here that says that the sum of the weight of all these partial products is equal to the weight of this output bit vector xy. And in comparison, SAT has no choice but to use a bit-level circuit to represent arithmetic. So should we be bit blasting to algebraic representations? Well, we found that this form of bit blasting actually did allow us to outperform some bit vector solvers for certain crafted inequalities. These inequalities contain mixes of multiplication as well as bitwise operations, since this is the weakness of bit vector solvers that we're really trying to target. Okay, so one of these inequalities, for example, was the following: kz is greater or equal to the bitwise and of x and k with z. Okay, and we found that rounding SAT was able to solve this up to 32 bits and pretty quickly, whereas the SAT-based approaches didn't do well at all with this. Okay, and this is actually kind of interesting because bit vector solvers are allowed to do a lot more high-level pre-processing to simplify the input bit vector formula. We can see that this simplifications didn't really help a great deal for this mixture of multiplication and bitwise operations. And on the other hand, we directly gave rounding SAT to a pseudo-Boolean instance, and this solver, it doesn't do any pre-processing at all. Okay, so to compare to the bit vector solvers, it kind of has one hand tied behind its back here. Okay, but of course, on the other hand, it does seem natural that an inequality-based solver would perform better on bit vector inequalities. It'll be an interesting future direction to find other multiplication problems where this cutting planes reasoning gives us this big advantage over SAT. So throughout this talk, we've used this lens of proof complexity to outline a different approach to verifying nonlinear arithmetic. So in particular, we've argued for taking a pseudo-Boolean approach to bit vector solving. While the small proofs that we constructed, along with our initial experiments, uncovered some of the potential of these solvers, it remains to be seen what happens if we really incorporate these ideas into an actual full-scale bit vector solver. Doing this, we could retain all of the sophisticated pre-processing routines found in current bit vector solvers, and all we would really need to do is replace this final SAT solver with a pseudo-Boolean solver. Possibly, bit blasting could be done algebraically instead of, or perhaps alongside, a bit-level circuit. So this seems feasible to implement, but the question really is, how will such a pseudo-Boolean bit vector solver perform on real-life industrial benchmarks that contain multiplication? So at the least, we can say that it seems likely that in order for this approach to really work in practice, we're going to need to improve cutting plane solving in general. Pseudo-Boolean solving is still relatively young, and many cases are known where current solvers are slow even though small cutting plane proofs exist. In fact, we weren't able to successfully solve any of the more complicated two-colorable identities, such as distributivity. But this is okay. Given the trajectory of improvements in SAT solving over the last 20 years, we'd hope that similar improvements could lie ahead for pseudo-Boolean solving. We see our work as a call to arms for pseudo-Boolean solver development, focusing on the features that will be useful for solving these kinds of bit vector problems. We hope that spreading the word on these multiplier problems could spur more work on new methods and heuristics for pseudo-Boolean solvers that could carry out more of this cutting planes reasoning in practice.